All right, but for now, let's continue with digital signatures. So first thing I'm going to cover is certificates. I already talked about these a little bit in the past talk. Certificates are not a cryptographic primitive, so don't think of these as any kind of mathematical magic that are going to work in some way that you don't understand. Certificates are dumb, right? They're not a stupid idea, but they are very naively implemented. Like they're a very obvious thing. Certificates are really just a witness statement, right, about some other key or keys, right? Some other public identity, some other public key. And the sort of interesting thing that you can do with certificates, because we have these key counterparts, we have the secret key, which you keep secret, public, which you keep sort of spread to the world. And we have the concept of signatures, and a signature can sign a message can be any data. Certificates are basically just, well, what happens when we put a public key as part of the message? Yeah. So the message becomes a public key and some other data, and usually some like format, language, lexicon to give computer systems or people some sort of metadata about this public key as certified by whoever owns the secret key that signed this certificate, right? And there's a reason it's called certificates. It's because this is really what a certificate is in the real world, yeah? If you do like, I don't know, you go and take up Taekwondo and you get your yellow belt, right? You'll get a certificate, and the certificate will be signed by the examiner that watched you do your examination, watched you do your yellow belt grading, and decided that you were good enough to have a yellow belt. Yeah, so it's literally a statement. I think this individual, Gavin, is good enough for a yellow belt, signed whoever, right? And then presumably they have their own certificate that says they are good enough for a black belt or whatever. They're good enough to hand out yellow belt certificates signed by, some bigger, some more certified person, all the way up to whoever the authority is on Taekwondo, right? Whoever the global recognized authority is on Taekwondo. And this is like, this is certificates, but done with digital signatures rather than, fancy paper and pens and calligraphy. So part of a certification system, it requires some degree of convention, especially when we're talking about very digital agile certificates. We need some sort of conventions on how these things can be issued, how they can be rescinded if desired, time limits, how long a certificate lasts for. Maybe it doesn't last forever. What maybe the format of the thing, in what order the fields come. Maybe a single certificate can represent multiple witness statements. Maybe it can have several public keys in there, right? Maybe you can say all of these people passed this grading, and you need semantics over all of these, all of this stuff. So you basically need a semantic language in order to define what these certificates mean. And they can be very simple, but it can also be fairly sophisticated. You've probably already seen examples of certificates in action. These, when you go onto an HTTPS website and it says, this is such and such a, you go to Google or whatever, and it says, yes, this is run by Alphabet Inc. And you can, why would I think it's run by Alphabet Inc.? Well, it can trace it back, and it says, well, such and such a, I don't know, maybe the US, the California certificate authority signed that it is Alphabet, and then maybe the US signed that these guys are allowed to sign that it's something, and then maybe the global registrar signed that this US registrar is allowed to sign things. Basically, the idea is you can trace it back, just like with regular cardboard, pen, calligraphy style certificates. Now, in Web3, we don't have, well, we try our very best at least to avoid authorities, right? So there is no like, with Taekwondo, there's a few like global authorities that decide, who the instructors and the examiners are, effectively. On Web2, there is, a global certificate authority, ICANN, for domain names. In Web3, we don't have these kind of centralized authorities, or if we do, they work under very exacting rules that are enforced in a decentralized, game theoretic manner. But we do use certificates still, but we use them in a much more decentralized way. Participants might provide certificates for their other keys, so it's clear that one key is controlled by a key that may not otherwise be linked, for example, with soft derivation, as we saw yesterday, is still controlled by the same identity. This would be one use case of certificates that are not based around not based around a central authority. But when you do come across certificates, the most obvious use case for them is, Web2 ICANN. Fine. Next, multi-signatures. Now, this is a bit of a hairy topic. There is a lot of quite deep crypto that deals with multi-signatures. In short, multi-signatures are basically making a single signature that means, or that is equivalent to, in some sense, many different signatures. And then there's all sorts of possibilities as to what those multiple signatures that this single signature means, how they could be constrained. Maybe they are signing the same message, but from different individuals, different public keys. Maybe they're signing different messages. Maybe there is a set of signatures of which there are a subset have signed it, but we don't know which subset. Maybe it's all of the set. Maybe it's only one of them. These are all different variants of multi-signing techniques, and they all have their uses. I'm not going to go super deep into the crypto because it is quite nuanced, and the APIs tend to be specific for each cryptography. But I will give an overview, so you've got an idea about what there is out there. Right. So that's not me. So we have three, roughly, three examples, right? The first one doesn't really belong here. It's here just so that you don't get confused with like multi-sig, multi-sigs that are non-cryptographic and think that they're cryptographic. They're not. But this is basically a non-cryptographic multi-sig, right? This is the cryptography part of the course, so it doesn't really belong here, but it's still a multi-sig in that it allows multiple signatories to have access to some resource. The difference between them is this one doesn't use cryptography in order to provide for there being multiple signatories. Rather, it uses some logic since this is a primarily sort of blockchain course, we would expect that logic to be on the blockchain. And basically, it's just like have 5 signatures come in, like count them, 1, 2, 3, 4, 5, okay. Then, okay, resource unlocked. Yeah, it's very, very simple logic, not cryptography. So we're not going to focus on this, but you might see multi-sig come up somewhere, If you do, that's why. You may see multisig come up somewhere that is not to do with cryptography. If you do, it's this kind of multisig. The other two are cryptographic, and we'll spend a little bit more time on those. Right, so yes, verify reinforced multisigs. We assume that there is like some verification logic, blockchain, for example, and this actually just checks what signatures have come in and make sure they're valid, and it counts them. It's really as simple as that. Could be a trusted company, but this is a blockchain course, so in general we would expect it's the blockchain that does it. But in principle, nothing stops it from just being a person that actually just checks. For example, could be a bank. You got a corporate account. Usually, if it's one of the main ones, it's not normally controllable by one person. It would be controllable by, like, I don't know, 3 people out of a possible pool of 5. That would be a pretty standard one. And there's like a person at the bank that checks, have 3 people signed it, yeah, of this 5, yeah. That's like a manual multisig, yeah. Well, this is sort of what we're talking about. The manual bit is done with oftentimes like logic, but it's not special cryptographic logic. It's just literally counting, yeah. There are, for example, in Substrate, there is a multisig module that does precisely this. Yeah? But it's not cryptographic, so don't get too hung up on it. It's very simple logic. Get annoying. Hello. Hello. Yeah. Hello. 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 All right. Cool. Yep. Right. So where were we? Yeah. So these kind of manual multisigs, they the main reason that you'd use them as opposed to a cryptographic multisig is essentially to minimize the complexities that the users have to do. And move those complexities onto the part of the system, the blockchain, the bank, whatever. This obviously makes the blockchain or the bank's job more complicated because they have to keep track of, like, for example, how many people have signed this thing. What is the thing that they are signing? But it's not usually an especially big a big job to do. It's just a bit of extra complexity. And potentially cost. Cryptographic multisigs. So, very different thing in terms of technology. This is where the fact that many people have signed something, many secret keys have been used, is represented through the mathematics of the signature. So we're used to I would hope by now, we're used to the idea of there being, a single secret key, signing a message to give a signature. Yeah, and then the signature can be checked that it was through a public counterpart of that secret, and the message, the signature can be checked to see if it's valid, right? We're fairly used to that idea. Well, with multisigs, we can still, the verification part, stage is the same. We still use a public key, we still check a signature, and we still use some sort of message, although it could be actually many messages. But the signing part, and in fact even the public key derivation part, can be substantially more sophisticated, much more complicated action. Now, in general though, it is about combining signatures, right? It's about having many participants, or many messages and one participant, or many messages and many participants, using their secret key in order to demonstrate that they have signed their message, right? That these individuals and these messages are in some way authorized, signed, the secrets have been used for them. When multisigs generate their keys, their public keys in particular, in different ways. Different multisig techniques will do them in different ways. So again, not going to go into too much detail here because each bit of cryptography is quite a long rabbit hole. But the point is that there may be quite sophisticated means of combining different participants' public key into a composite key, a key that's composed of all of these different participants. Yeah, and it's usually some fairly weird mathematics, where you're like combining them under some, or combining several under some mathematical operation. Now let's look at a specific example, threshold multisigs, right? Cryptographic threshold multisigs, because this is the one that probably has the one of the biggest use cases in terms of actual users rather than in terms of systems. So a threshold multisig is basically a means of basically doing this bank account thing, right? A means of saying, well, we have 5 signatories. We want to have a way of succinctly, right, knowing whether 3 of them have signed a particular message. And basically the way it works is you devise a new public key, right? So you take the 5 public keys, you take the constraint that 3 of them must have signed a message, and you combine this constraint with the 5 public keys in some crazy mathematical magic, and you end up with a new public key, right? This public key, it looks like just any of the other public keys, same size, but it means that if you see something that is signed with this public key, then it means that 3 of these 5 public keys have themselves signed the same message. Yeah? Now the cool thing is that because it looks like any other public key, and because it verifies a signature just like any other public key, you can use it on systems that weren't even necessarily designed for multi-signature, right? You can use it on systems like Bitcoin or Ethereum or whatever. And that's pretty cool. In order to sign the message, and often in order to create the the public key, there have to be some, certainly in order to sign the message, there has to be some quite complicated kind of dance between the participants, right? So it's not a like a case where, you know, they just put their signature in and then with their public key, with the secret key that they control, and then somehow it just gets transformed. It's like they actually have to, first one does one thing, then the next does another thing, then the third does something else, and then they go back to the first and they do something with the data that has come from the other two, and so on and so on and so on and so on and so on. It's an interactive protocol, right? Often. And I say often because different cryptographies do this in different ways. Sometimes the interactive protocol is very interactive, sometimes it's much more simple. For example, you know, depending exactly on how you, whether you're using like ED 25519 or SR 25519, and depending on precisely which implementation you're using, maybe it's like you have to go around 3 times in the loop, or maybe you have to go around 2 times in the loop. And it's, you know, it's very much dependent on the implementation, and there isn't like a specific set of details I can give which would work for all cryptographies. Yeah. But indeed, so MPC, multi-party computation, right? This is basically where many different parties each help with a particular piece of computation, oftentimes not knowing what the other parties know. Yeah. So they all sort of do their own little bit of work on their own bit of information, and through all of them a result arises, but none of them could have created that result alone, and usually none of them, by the end of the computation, could repeat that calculation, right? So secrets are kept secret, basically. These protocols that allow you to do signature aggregation or these threshold multisigs, they can be quite brittle. By which I mean, if you have someone who's a participant that is malfunctioning, potentially malicious, then it can break the overall process. That can be problematic. You might get DOSed, or you might get, I don't know, whatever. You might get DOSed. Yeah, I think that's probably it, actually. Okay, good. There may be depending again on the cryptography, the means of determining this public key that represents the threshold signing may be a difficult operation as well, right? It may be the same level of sophistication, multi-party computation, all of the parties sort of getting involved, signing something, doing some random operation, combining the result in some predetermined sort of multi-party algorithm. And in principle, it could result in one party who is malicious sort of breaking the entire process. Yeah. So it's, as I say, it's kind of brittle. But if you can make it work, then you end up with this, you know, really cool outcome. In the case that you control all of the keys, like all of the keys are sort of known to be controlled by well-aligned parties, it's usually not such a big problem. For example, if you're opening a bank account and there are 5 of you and you want to have a sort of 3 of 5, or if it's a company account or whatever, then you're all probably going to cooperate. Yeah, it's not going to be a big issue. If it goes wrong the first time, you're just like, oh, that's strange, and then you do it a second time and it's fine. But if you're on like a decentralized system where, you know, no one really trusts anyone else, then this can be a bit of an issue, right? Because you only need one bad apple in the set, and they can make stop this stuff working, and they can't always be identified as well. Again, there are some protocols where they can be identified, some protocols where they cannot. Finally, this sort of thing is incompatible with, oftentimes, with other mechanisms or facilities that the cryptography would otherwise give you. For example, hard key derivation. Can make, actually, I think I've got a slide on that. Yeah, okay. So let's look at a specific cryptography. This is the one that Polkadot uses, Schnorr. That's what the S in SR25519 stands for. So Schnorr signatures are great because they allow us to do threshold multisig relatively easily. If the I think potentially in just 2 rounds. So like go to participant 1, go to participant 2, go to participant 3, take the result, go back to 1, 2, 3, and then maybe there's some other flip that you have to do, but basically that's it, and that's your signature. That's the sort of thing that we can do with Schnorr signatures. And as I said before, they look like any other regular kind of signature. So pretty cool in that regard. If you're doing certificates, Schnorr, these kind of cryptographic multisigs are great because you don't need to store anything on chain. Otherwise, you probably need to store stuff on chain, or at least you'd have the certificate and have to have like many different signatures at the bottom, which could make them bulky. Using this stuff, there's just one. And if you're talking about like, I don't know, a decentralized system with like 1,000 participants, and you want to, it's like a 2/3, like a 667 out of 1,000. You don't want to have to store 667 signatures for every certificate, right? Because signatures are like, I don't know, 65 bytes or something. It quickly gets quite big, especially if you're if you're wanting to like pass these things around quite freely. You're suddenly starting to have to pass like huge amounts of data. If it's just one signature, that's a massive reduction. It's a 667 times reduction in bandwidth, more or less. There you go. Right. So there are, particular issues with using Schnorr multisigs, but it basically just makes implementation more of a pain. Right. One other type of crypto that provides multisigs, BLS. Now BLS is like has some pretty crazy stuff going on, pretty magical stuff going on. And again, I'm not going to get too deep into it. BLS isn't really used in Polkadot yet, although it will be very soon, TM. BLS, I guess in some sense, represent a bit of a holy grail for multisigs, in that they, maybe not holy grail is quite the right word, but kind of a Swiss Army knife, right? One of these like very, very flexible systems for doing so. One of the big points is that the signatures can be aggregated without any like without any dancing happening before the aggregation happens, right? So you don't need to like have any special multi-party algorithm to work out what the public key is, for example, as you would do with other systems. It can all be done just sort of just in time. The biggest issue with BLS is its speed, right? It's very, very slow, like 100 times slower than Schnorr. But the coolest thing with BLS is it can be used to verify or to aggregate, so to create a single signature from many signatures where the message and the signer are different for each message signer pair, for each signature that it's aggregating. And because of this, you can basically like take a big long list of transactions, say 1,000 transactions, 1,000 signed statements, right? Where each signature is for a different signer and a different message, right? A different transaction. And then you can create a aggregate signature. So just remove all of those signatures and create just one, replace them with just one signature that means exactly the same things, exactly the same thing as all of these guys, cryptographically speaking, mathematically speaking. What I mean by that is you can verify just this one thing and be sure that each of these signatories signed each of their messages that they're associated with. Yeah? And that's like really useful. I mean, that's great. It's great for two reasons. It saves you on bandwidth because you're not storing all these signatures anymore. You're only storing one. Yeah? And it's great in terms of time because although BLS, it might be 100 times slower than in each individual Schnorr signature, if it were done with Schnorr. If there's 1,000 of them, then it's still 10 times faster. Yeah? Because instead of 1,000 Schnorr signatures, you've only got like one thing that's 100 times the speed of the time as a Schnorr signature. Good. Oh, there you go. So multiple signatures with multiple public keys for multiple messages can be aggregated into a single signature. For this reason, it's useful for stuff like consensus systems, particularly for like transaction signing evaluation aggregation. The main, I think the main thing it will be used for in Polkadot would be sort of two things. But the first one will be the combining transaction signatures, and the second thing will be used for second point it will be used for is I think Grandpa, which is basically a consensus scheme, trying to aggregate these as it happens 667 signatures into one. Right. When you're using BLS for threshold, then you do still need the distributed key generation, this dance that everyone has to do, and that's potentially quite tricky. Soft key derivations, and they become insecure. And as I said, like verifying can be hundreds of times slower than the equivalent thing in Schnorr, but this, depending on how you're using it, might not be such a big issue. Good. I think that's probably it for Schnorr and BLS. Right, one final little thing while we're on the signing stuff. Ring signatures. So ring signatures are basically a anonymity protocol that allow a number of different signatories to make an aggregate signature without knowing which of them signed what, right? So basically, it's the cryptographic equivalent of having 10 people, I don't know, stand in a ring, have a hat in the middle, right? Each of the 10 people write an instruction onto a bit of paper, fold it up. Maybe they don't use their own handwriting, I don't know, they type an instruction onto a bit of paper, fold it up, put it in the hat, right? Now you've got 10 instructions, 10 people, one from each person, but you don't know which instruction matches which person, right? That's basically ring signatures. You just have 10 instructions, like 10 messages. Each message is signed by one participant. You know who the 10 participants are, but you can't match the message to the participant. Obviously, if these messages are things like pay such and such $100, pay such and such $500, it's not going to work if the dollar amount is different, right? Because then participant 1 who wants to pay $100 from their account might, and participant 2, well, they might want to pay $500 from their account, and if you can't match these individuals anymore, then presumably you just pay into a big pot, so each of the participants pays their money into a big pot, but now suddenly participant 2 is taking 500 from the pot, and participant 1 is only taking 1. Like, it's not clear who should be putting how much into the pot, basically. It works quite nicely when the instructions are, in terms of value at least, all the same, right? So you might have a different destination for the payment, but if they all want to pay like $100, then it works super well, right? Because they all put $100 into a pot, they all sign where they want $100 to go to, and then the pot pays out to each destination, and you can't link destinations with the person who's paying, right? And that's sort of more or less how it's used for. Zcash uses Ring. You might have heard of Zcash, anonymity, sort of a privacy feature focused version of Bitcoin. Uses ring signatures together with some more advanced zero knowledge proof, basically to make the entire chain history be an anonymity set. But there will be more information on zero knowledge proofs in a follow-up talk. Good. I'll take some questions, but I reserve the right not to answer them because this is not my forte. Any questions?
Hey, Gavin. So you mentioned earlier that multi-party computation has the issue of being susceptible to malicious actors. Mm-hmm. Does this also apply with a threshold? So if you need 5 out of 7 keys, can only a single malicious actor prevent something from happening or cause a denial of service attack? Or does it have to be like more than the needed threshold?
In practice, it would have to be more than the needed threshold, just because you could instigate a protocol where you disregard, so you run through each of the 7, you disregard that signatory, and the other 6 just try to sign it, right? And if that doesn't work, you disregard 2, and each subset of 5 just tries to sign it. Yeah, so you can basically, under that protocol, it will take longer, but you can withstand up to 2 signatories being malicious, because you just ignore them, right?
Got it. Okay, thanks.
Yeah.
I have a question. Maybe this is a stupid question, but I'm just wondering what the point. So I get the importance of BLS, but I'm wondering what the point of multi-sig is. If it's different than, say, Adi Shamir's secret sharing, where you have to have a certain number of, you meet some threshold and then the secret unlocks. Mm-hmm. How's this different from that?
It's actually, it covers a similar use case. So with Shamir's secret sharing, you split a secret up, and you can reconstitute that secret through a subset of the parts that you split it up into. The nice thing about this is that it gives you a way of actually making a signature when the signatories, so those parts, don't have to collaborate with each other in such a way that would divulge their part. So if you control all of the parts, it doesn't matter so much, because there's only one, you already have access to all the secrets anyway. But if the parts are owned by many different participants, and especially participants who do not trust each other, then this becomes very useful because you can create a signature without any of those participants having to trust all of the other participants or some large subset of the other participants.
Okay, that helps.
Is there different weights that can be attributed to the different participants of multisig?
Not directly, but you can give one participant 2 shares of a multisig,
Okay.
if you want to
Thanks.
do it that way. Okay, and I will go over a point brought up yesterday. The question was, where are we? All right, let's do it. Let's use this diagram. Bit of a mess, but anyway. The question was, can the public key always be derived from the secret? Answer is in 2 parts. The first part is it doesn't really matter. The secret, the mathematics of it is less important as to the information pathway, the information logistics of it. And the information logistics are that you create the mnemonic, and the mnemonic is the secret, right? The mnemonic, or maybe the seed that the mnemonic is, that the mnemonic derives, but that seed is the secret. Now, if there is some other secret that actually is used for signing the message, that's sort of an implementation detail. And if that secret happens not to be able to create the public key, then that's sort of an implementation detail, because the real secret is the first piece of secret information. And that first piece of secret information can always, by definition, create the public key. Yeah? The second point to make is that though these are sort of, though signing and encrypting are a sort of symmetric operations, there is a sort of a potential difference, right? A sort of notable difference. With encryption, you're not given, with decryption, you're not given a significant, you're not given the message in the first place. This is not a case where you're given the original message and the encrypted message, and you're asking whether the public key encrypted this message. Yeah, that wouldn't make sense. Yeah, we're not trying to verify. That would be a verification operation. We're not trying to verify that encryption happened. We don't know the original message, and we are trying to derive it from the ciphertext, from the encrypted message. This means that if the public key were used to encrypt some plain text, and we say that the secret key can definitely be used to decrypt it, then the public key could not have placed any more information, could not have access to any more information than the secret key has access to for its decryption. Because otherwise it wouldn't be able to decrypt the message. This is different to the verification stage, where it's possible that the secret key in creating the signature actually has access to more information than the public key in verifying the signature. Because the public key isn't being asked to derive any information, it's simply being asked to see whether this operation was legitimate, right? It's basically it's returning either true or false. It's not trying to recover some large piece of information that went in the first place, in the same way that decryption is trying to do. Now, this doesn't mean that, therefore, the public key can always be derived from the secret key, but it does mean that the public key could not have access to any more information than the secret key. It could still potentially be some weird function where they can only be created together, just because of the underlying mathematics. But as I said in the first place, I don't want to get too hung up on the underlying mathematics. The main point is that these two things are not created as a pair. They're not like forged from the world as a pair. First, you start with your secret material, a mnemonic or a seed or whatever, and then from that you derive your identity, right? And whether, precisely how you get from your secret material to encrypting a message or verifying, sorry, not encrypting a message, decrypting a message or signing something, whether there's a step where you create a sort of sub-secret, that's kind of part of the crypto implementation and doesn't really need to be considered when we're talking about, engineering aspects, when we're talking about what data you need to store and who you should be giving access to. Good. All right. That concludes digital signatures.